Hi, my name is Florian Streibelt, and in this talk I want to present our work on name resolution in an IPv6-only world. But first, I would like to thank all my co-authors, Patrick, Franziska, Carlos, Anja, Oliver and Tobias, for their support in this project. Without you people, this would not have been possible. But now, without further ado, let's jump in. What's this all about? If you use a tool to check if a website is IPv6 enabled, confirm that the hostname resolves to an IPv6 address and you can ping the server, you would expect the website to work when using IPv6 only, right? However, when pointing your browser to that URL, this is what can actually happen. Your browser tells you it cannot find the website. But how can that be? We just confirmed network connectivity and name resolution to work. So let's check where it breaks. In this case, accessing the website failed because the name servers of the domain have no IPv6 addresses. And to identify these hidden dependencies on legacy IP, we are measuring the IPv6 resolvability in a strict IPv6 only setting. But first, let's briefly refresh our DNS knowledge. This visualization of the domain name system looks pretty familiar and can be found in each and every textbook on networking. However, assuming we know nothing about DNS, it contains some interesting questions. When resolving, we are supposed to start at the root, but how can we actually find that root? How do the root servers know which TLDs exist and which don't? Why is there a zone split at example.net but not at .nameexample.com? Almost all of these questions can be answered by looking at DNS records in the DNS zones. In the context of this presentation, DNS records define the location of zone splits and thus which zones exist and which name servers hold authoritative information on these zones. However, let's look how this is supposed to work in practice. For this, let's look at a very small part of the DNS tree, just the root and the top-level domain.net. In order to start at the root, a recursor has to know which name servers are authoritative for the root zone and how to contact them. This is achieved using a text file called root hints that is usually part of the resolver software distribution. Because at this stage we have no working DNS yet, the IP addresses also have to be included in that file. Let's now look at our .NET zone. Here we only need DNS resource records for now. Note that this zone definition is present on the authoritative name servers A and B GTLD servers.net and in reality also contains all the other zone data. In order for name servers to know which child zones are delegated, these NS resource records from the child zone have to be copied into the parent zone. So another question from our previous slide is answered. But we also learned that some data has to be copied from the child into the parent zone manually. Looking closer, however, on what we have just copied, we will notice that we have created a circular dependency because the GTLD servers.net zone is part of the .NET tree, and we call this to be in bailiwick. The fix for that again is manually providing the missing information in the parent zone in the form of glue records, breaking this dependency loop. However, this requires out-of-band communication because it is not part of the DNS protocol, and this means we need coordination between the operators of these different zones. This brings us to the question, what can go wrong here? We identified 5 root causes for failing IPv6-only resolution, of which I will present 2 in detail later. The first case is pretty simple. No name server of a zone is IPv6 enabled. Recall the Wikipedia example from earlier. The second case is missing glue records for IPv6 in the parent zone. The third case is a mismatch in parent and child zone, triggering security measures in some recursor implementations. The fourth case can be hard to spot. Here, the authoritative name server of a zone cannot be resolved because the zone their names are part of cannot be resolved correctly. Please note that these misconfigurations are not mutually exclusive and they are also not IPv6 specific. But falling back to using IPv4 when IPv6 is unavailable makes them especially hard to notice. Most importantly, from the tree structure of DNS follows that one misconfigured zone will break all child zones in its subtree. Let's now look at examples for cases 2 and 4. The first example is missing glue records. Our example.com zone depicted here is configured perfectly with .A records for all names. But looking at its parent zone, we see that the glue records for IPv6 are missing. On the right, you see how a correct configuration should look on the internet. Here I sent a query for DNS records of one of my domains to one of the authoritative name servers for the .NET top-level domain. Note how the additional section contains A and .A records for all name servers that are in bailiwick, but not for the some server one, which is in a different top-level domain. The second example shows how indirect dependencies can make misconfiguration very hard to spot. Again, look at a perfectly configured example.com zone that uses two external name servers in some DNS.tld. The delegation in the parent zone also is set up correctly. And the name servers have Quad A records configured in their zone. However, the zone of the name servers SumDNS.tld uses name servers in yet another zone, and this zone apparently cannot be resolved using IPv6. This breaks IPv6 resolution, as the IPv6 addresses of the name servers cannot be retrieved. Let me now give a quick overview over the datasets we used. Our passive datasets contain the Farsight SAE dataset, collecting DNS requests and responses at recursive resolvers whenever a cache miss occurs. This ensures minimal privacy impact, and our dataset spans over about 7 years. The second passive dataset consists of zone data of almost all zone files we could get our hands on. This allowed us to compare the data captured in the wild with more than 101K zones as of August 22. We then used active measurements to confirm our findings, executed on 7 days in October 22 based on the Alexa Top 1 Million list matching the latest data from our passive dataset. Our methodology is straightforward. We just implemented recursive DNS resolution in various ways. Why can we do that with our passive datasets? With clients implementing happy eyeballs, most of them will crave for A and Quad A records, making these available in the Farsight data, and glue records are being part of DNS responses anyway, so they are being collected as well. The zone files, on the other hand, contain all the information the authoritative name servers have available on their zones, so they of course can be used for that purpose. For the active measurements, however, I implemented a recursive resolver over the time span of 3 months that queried all authoritative name servers of a zone and combined the answers. With the publication of the data already in mind, I also requested the start of authority MXTXT records and bind version in ID from the KS class. Because I think that we should discuss the system design of our measurement tools more often, let me walk you through our system. It consists of 3 parts: 4 DNS probe processes, 2 DNS caches for the responses split into IPv4 and IPv6, and worker processes implementing the actual measurement methodology. The DNS probes were located on a dedicated machine in front of any connection tracking firewalls, and these probes talked DNS to the internet. The outgoing requests peaked at around 2.7K per second, and these probes had to implement all of the nasty details like rate limiting, retries, truncation, fallback to non-EDNS, and so on. The caches store all outgoing requests and the answers received, including errors, timeouts, and retries, making sure that we limit outgoing requests as much as possible. All of the internal communication uses a minimal JSON-based protocol without any overhead of HTTP or RPC, using one long-standing TCP connection. Although I implemented the ability to reconnect, in the end the connections between caches and probes had been up for 10 days continuously. The workers were started using XArgs after splitting the Alexa list into chunks of 200 entries, limiting the amount of lost data if one of the workers would crash. Workers and caches had been co-located on the same host to minimize latency. Because a comprehensive visualization of DNS is almost impossible and looks more like modern art, let me just present 3 main takeaways from our work. And given the limited time and because you can find all of the meat in the paper and I want you to read it, let me just highlight the main message from these plots. Over time we see more and more zones can be resolved using both IPv4 and IPv6, and depending on the subset of zones, you can even see very high fractions of dual stack support, which is nice. And the fraction of IPv6 resolvable zones increases slowly but steadily, so in about 30-40 years we should be there. If we now zoom in on the zones that cannot be resolved using IPv6 and look for the reasons, we can see they mostly fail because of bad parenting, because of their parent. Without a working parent zone, it does not matter if the child is configured correctly, but indeed, mostly parent and child are both failing IPv6 resolution or they are both configured incorrectly. Finally, let's take a look at centralization, and when we plot the numbers there, we can clearly see by the dominating colors orange, yellow, and blue that the top 10% of NS in their respective group are responsible for most, if not all, zones. While for TLDs we are not surprised, looking at the Alexa domains, being able to identify the one top NS set is astonishing. So a very small set of name servers and thus operators runs most of the DNS infrastructure, which can also be seen as chance to get more adoption by convincing these few operators. So why is this form of misconfiguration often hidden in plain sight? Although we know that all sorts of failures occur all the time and we need monitoring. The answer lies in the design principles of DNS. It was meant to be robust and includes countermeasures against failing servers. As long as one authoritative name server of the zone can be reached or cache TTLs are not expired, name resolution will work. This means each monitoring solution has to take these mechanisms into account. The example shown here is not sufficient to monitor availability of DNS resolution. It will even make it harder to detect outages by regularly refreshing the cache content and resetting the TTLs. Before wrapping up, let me quickly talk about some caveats. Whenever we are measuring, we have to confirm that what we think we measure and see is actually what we do measure. Some artifacts might look like a misconfiguration, but they are just part of a migration or maintenance. Missing glue records can simply be explained by first testing the change internally before adding glue in the parent zone, where it's hard to get removed again because the zone is controlled by a different organization. And I learned that such a change can take weeks to get applied. On the other hand, sometimes we think that observations are part of a very clever operational practice, when in fact they are just actually the result of simple oversight. And given the complexity of protocols today, are we always supposed to know them better than their inventors? Remember to stay in touch and ask people why things are the way they are, and stay curious. With that, let me summarize the talk and look at future work. We conducted a long-term passive measurement study including a root cause analysis for broken IPv6 delegation in an IPv6-only setting, and our findings are confirmed by active measurements. In August 2022, around 45% of considered zones are not resolvable using only IPv6. Most commonly, the zone's name servers or parent zone's name servers are unresolvable. Our recommendations include monitoring IPv6 across the entire delegation chain, and we want to point out that the IPv6 readiness of the web may be impaired by non-IPv6 resolvable domains, making web assets unretrievable. For the future, we suggest scans of IPv6 resolvability of web assets to raise awareness with operators and assess the impact on the web. Our next steps will include code polishing and publishing our implementations as open source. We also will provide a reduced toolset for operators, enabling them tests from within their networks. With that, I thank you for watching this recording, and please feel free to reach out if you have any questions. Thank you for your attention.